Special pleasure to announce the next speaker, the lady speaker actually. She comes from GIA Innoter, Elena Kravtsova. Those of you who have been at Dracor's conferences before, over the past 3 years, Elena was reporting on the From Imagery to Map conferences about the precision of canopas and on how real imagery is done. To be totally sincere, we hope that we will be managed to show the results of actual processing from resource P at this conference, but unfortunately we received the order for this work from Roscosmos only last week, and the results will be submitted to Roscosmos tomorrow. So basically we were lacking just a couple of days to present these results at this conference. Anyway, as long as over the past 1 year of this conference many things have happened, they launched not only Russian satellites but also other satellites. We thought it would be interesting for professionals to see a comparative analysis of other satellites, also not only Russian satellites. And Elena done some work on this, and she's going to present it now.
Good afternoon. So this is going to be comparative studies of accuracy of images obtained from new spacecraft. Thank you. In recent years, there's been a rapid development in remote sensing data, especially in high and super high resolution. Particularly the emergence of new satellites in orbit, development of software to process spaceborne imagery, a wide diversity of imaging systems required taking into account their accuracy characteristics to ensure conformity between tasks and the results, to select optimized parameters and to deliver products with required accuracy. Geometric accuracy of orthophoto plans created based on the high and super high res images is a determinant in making decisions whether or not then they can be used for large format mapping, map updating, and photocadastral plans. The purpose of the study was to examine and compare geometric accuracies of end products of orthophoto plans using a photo mode. So I'll start with ZY3. It translates as a resource. It's used for remote sensing purposes, obtaining high-quality images for the purposes of land users, land monitoring, environmental and urban development. This one was launched in 2012, January the 9th. You can see some technical characteristics of it. It was put on sun-synchronous orbit of 505 kilometers with inclination of 97 degrees. The satellite has 3 panchromatic cameras with super high resolution and multispectral sensor. The cameras are separated by 22 degrees, facing forward and backward. The back camera has resolution 3.6 GSD, and it can scan the strip with 52 kilometers swath. The nadir camera has resolution 2.1 meters, and it scans a 50-kilometer swath, and multispectral camera has 5.8 GSD with a scanning capacity of 52 kilometers. For study purposes, we used a 2-meter panchromatic image and a stereo pair for the western coastline of Australia. Image dates back to 2012, August 16th. It's 1A image and RPC coefficient. The difference in heights here in this area is up to 400 meters. There are 14 ground control points. The elevation matrix was based on vectors and pickets generated interactively based on stereo pairs. The accuracy of matrix is about 2 meters. These are the outcomes of photogrammetric processing in 4 stages. First, we looked at the original model when all the points were checkpoints. The maximum error was 9.6 meters. The RMS was 8 meters. Based on external orientation, the average error, the maximum error was 2.2 meters. The geometric accuracy of orthophoto plans was estimated using mosaic. It was 1.4 meters from RMS, and 2 meters was the maximum error. Also, we did secondary verification using independent points. The error there was 4 meters maximum, and RMS was 2 meters. The next satellite is TH, the Chinese satellite designed for a wide range of applications. It was put in orbit in 2010, August 24th, 500 kilometers high, and the inclination angle is 97 degrees. It uses a stereo camera that delivers images in triplet mode, resolution 5 meters, swath 60 kilometers. There is nadir panchromatic camera with the resolution of 2 meters and a swath of 60 kilometers. There's also multispectral camera, 10-meter resolution and 60 kilometers swath. For these images taken from the satellite, we took one nadir image for Moscow region, 1B RPC coefficient and corrections. We used 14 GCPs and a stereo pair belonging to 1B level. We generated an elevation matrix with 10-meter spacing interactively using vectors and pickets. The height difference is up to 200 meters in this section, and this is the result we got. For RPC, the error was 44 meters max, RMS 34 meters. External orientation results: maximum error 4.8 meters, RMS 2.9 meters, nearly 3 meters. The accuracy of orthophoto plans is 1.4 meters, RMS is 0.7 meters, and secondary verification showed the maximum error of 5 meters and RMS of 3 meters. The next satellite is the one that was launched on the 9th of September 2012 as Spot 6, put on sun-synchronous orbit of 694,000 kilometers, inclination 98 degrees. The satellite has a lot of capabilities. It uses panchromatic camera with a resolution of 1.5 meters, swath 60 kilometers, and multispectral camera that uses 4 bands with resolution of 6 meters and swath of 60 kilometers. From this satellite, we used imageries for Nenetsky autonomous district. We used one stereo pair from July 23rd, 2013, with angles of 12 and 15 degrees. For referencing, we used only 6 points. The elevation matrix was generated manually using stereo pair. Accuracies for RPC: maximum error is 15 meters, RMS is 14 meters. External orientation: maximum error 3 meters, RMS 1.8 meters. Accuracy control of mosaic: maximum error is 3.7 meters, RMS 2.7. And independent checkpoints, we got the maximum error of 2.7 meters and RMS 2.4 meters. And the last satellite to be covered in my presentation is South Korean multi-purpose satellite CompSat 3, launched on May 17, 2012, on the orbit of 685 kilometers. This satellite crosses the equator not in the morning, but at noon, around 13:30. It is equipped with a high-resolution camera of 70 centimeters and swath of 15 kilometers, and multispectral camera with 2.8 meters and swath of 15 kilometers. For the purpose of the study, we use 2 1R images forming a stereo pair for the territory of Spain. From May 13, 2013, the height difference in this section reached 700 meters. Ground control points were borrowed from orthophoto plans taken from 5,000 meters stereo orthophoto. RPC error is 68 meters max, and RMS is 63 meters. External orientation, maximum error is 2.8 and RMS is 1.6. Orthophoto plan accuracy, maximum error is 1.4, RMS is 0.6, and secondary control of orthophoto plan showed maximum mistake of 1.5 and RMS 1 meter. In conclusion, I would like to share with you a summary table showing differences in coordinates for different points. The initial points were the ones taken from GPS measurements, maps, orthophoto plans, and the difference of coordinates was regarded as a sum of systematic geometric errors, RPC coefficients, elevation matrix, and there are 2 options for elevation matrix generated manually using a stereo pair, and elevation matrix that is available to any user. This is Astro matrix. From this data, it follows that the generated orthophoto plans, digital orthophoto plans, based on stereo pair elevation matrix, has definitely better accuracy, especially for the areas with prominent relief. And images from COMPSAT 3 can be used for 5,000 scale, for spot and ZI for 10,000 scale, and from TH for 25,000 to 50,000 scale. When using Astro DM, the accuracy is worse. And then the scales involved are much smaller. All right, thank you very much. Are there any questions? Rustem Zhetpisov from Kazakhstan. I have two small questions. What did you use as ground control points in all these projects? And you had two graphs in independent estimation, orthophoto plan 1 and orthophoto plan 2. What is the second one? Yes, indeed. I didn't tell you about this individually. I put it in one summary table. The second one was for Astor. We use different ground control points. Some were provided by the customers. It was a presentation involving images that we were commissioned to deliver. Other ground control points were taken from maps and orthophoto plans, more accurate orthophoto plans involving aerial survey. That's where we got them. Any other questions? No further questions. Thank you, Elena.